Today we're going to be reviewing using the derivative to solve problems, and specifically we're going to be looking at optimization problems. Optimization means that we're going to be figuring out what would give us a maximum value or a minimum value. Now, excuse the format, this block that says 1 up here should have actually been here, so we're going to move down there to start the steps for solving an optimization problem. So number 1, we have to determine the quantity or the variable that is to be maximized or minimized. Number 2, this is where we want to sketch a picture of what's going on. We want to assign variables. For unknown quantities. Now, since we're trying to maximize or minimize some certain quantity, we need to write an equation that represents the quantity to be optimized. Optimized just means we want the optimal, the best value. And think about it, sometimes we want to maximize that, we want to maximize profit, that type of thing. Sometimes we want to minimize, like minimizing costs in businesses. So there are going to be times if the primary equation has more than one variable, so more than one unknown, you may need a secondary equation. So that substitution can be made so that the primary equation only has one variable. So once you have that primary equation that you're going to be optimizing, and you only have the one variable that you're seeking to optimize, we want to find out the maximum or minimum value. So what we're going to do is we're going to differentiate. And determine the maximum or minimum values. When do maximum or minimum values occur? Well, they occur when the derivative equals 0. But to know whether it's a maximum or minimum, well, maximum is going to occur when you go from positive to negative, and the minimum is when you go from negative to positive. So we've got to focus on those number lines again, plugging in values to see if we get a true maximum or minimum. So example 1, a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with a maximum volume? So number 1, we want to find the quantity that we're we're optimizing. We want a maximum volume. So next step is to draw a picture. So we have an open box with a square base. We have a square base. So this base, and that means these sides are equal, so I'm going to do this as x and x. And then, that didn't tell us anything about the height, so that'd be a y. And so we need a formula, primary equation that represents what we're going to be optimizing. So we're maximizing volume. So volume is length times width times height. So that would be x squared times that height of y. Now, we do have two variables there, so we're going to need a secondary equation. So let's see what other information we know. Well, we know something about the surface area. So let's think about the surface area of this box. Well, it's an open box, so there's no lid there. There's a base. So for the surface area, there's a base, which is that x squared, and then we have four sides. This side, and the back, and the other side here. And those are all the same dimensions, length and width, x, y. Now we know what that surface area equals. They told us that was 108 square inches. Now, we want to get this to one variable. I kind of like having x's as my one variable. So I'm going to solve this for y. So if I want to get y by itself, I'm going to start by getting that term by itself. Divide by 4x. So now we have an expression for y. So what we can do is use substitution, replace this y with this expression. So now our volume formula will be volume equals x squared times our expression for y, which is 108 minus x squared over 4x. Now remember, we can make this into a fraction, so we can multiply across and then divide by 4x. So I'm going to clean this up a little bit. If I multiply across, that's going to be 108x squared minus x to the 4th over 4x. Now I know I can differentiate that. I could use the quotient rule, but I really don't want to. Let's make it even prettier. Let's divide by 4x. So 108 divided by 4 is going to be 27. X squared divided by x is x. Minus, that's going to be 1/4 x cubed. That's a lot easier to take the derivative of. So when we take the derivative, v prime is going to be 27 minus 3/4 x squared. Now, if we're trying to find the maximum volume is going to occur when this is either 0 or undefined. Let's set it equal to 0. So I would get 27 equals 3/4 x squared multiplied by 4/3. 27 times 4/3 going to give you 36 equals x squared. X equals plus or minus 6. Now, does it make sense to have a negative 6 for our length here? No, so we're really going to be looking at 6. So let's make a number line. This is a number line for v prime. We're plugging in to our v prime here. So here's 6. If we plug in something to the left of 6, so let's say 4. If we plug in 4, That's going to give me 16. 3/4 of 16 is going to be a 12. It's going to be a positive answer. If we plug in something bigger than 6, let's say 10. 10 squared is going to be 100. 3/4 of 100 is 75. That's going to be negative. So we're going from positive to negative. That means 6 is a maximum. So the volume is a maximum when x equals 6 because the derivative of v changes from positive to negative. So, to answer the question now, so we proved that that's going to be a maximum, what dimensions will produce a box with maximum volume? So now we need to list out our dimensions to truly answer the question. And then we actually need to find what is the maximum volume. So if this is 6, so we have, let's plug it in to here to find the height of that box. So we already know we have 6 inches by 6 inches. So that's going to be 108 minus 36 over 24. It's going to be 72 divided by 24. That's 3. Now we need to know that volume. So you would take your 6 and plug it back into your volume. Or, now that we know our dimensions, 6 times 6 times 3 would give me 108 inches cubed. Make sure you put your units. So that to actually answer the question, we need to make sure we listed out the dimensions and the volume. Here's the next example. A box is to be built from a rectangular piece of cardboard that is 25 centimeters wide and 40 centimeters long by cutting out a square from each corner and then bending up the sides. Find the size of the corner square that will produce a container that will hold the most amount of soup. Most amount of soup. What are we going to be optimizing? Well, we're going to be optimizing volume. So let's start with a picture. So we have a rectangular piece of cardboard. .25 centimeters wide and 40 centimeters long. We're going to cut out a square from each corner. And so the squares, let's call the squares, let's say x by x. X by x. X by x. X by x. So we're cutting out a square that's x by x big. And if we fold out the sides after we cut out those squares, we end up with a box. So this long piece here, so we fold it up, notice that that's going to be the new side that would be here. So that whole thing was 40. We cut out a piece x here, cut out a piece x here. So this is going to be 40 minus 2x. This side here, 25 was the whole side. Cut out an x. So remember, we're folding up along these little dotted lines. This would be 25 minus 2x. The height of our box would be that x, because these pieces would have gotten folded up. So we're trying to maximize volume. Volume is going to be length times width times height. So x times 40 minus 2x times 25 minus 2x. Great, we have only one variable. Now, I could use the product rule here, but it's going to be a lot easier to take the derivative of if I multiply everything out. So 40 times 25 is going to give me 1,000. 40 times negative 2x is going to be a negative 80x, negative 50x, and a positive 4x squared. Now let's multiply by the x. We could also combine like terms here, couldn't we? That'd be a negative 130, and now it'd be an x squared plus 4x cubed. I like to write it in order. So now, we have the formula for volume, and we're trying to get the most amount of soups. We're going to maximize it. So we need to take the derivative. It's going to be 12x squared minus 260x plus 1,000. And we're going to be setting this equal to 0 so that we can find that critical value that could be a maximum or minimum. Let's see, what can I do first to make that prettier? Well, I think they're all divisible by 4. And since I do have it set equal to 0, I can divide both sides by 4. Now I need a factor. If you need help factoring, you can use the factor box. The two missing terms are going to add to be a negative 65, but multiply to be a 750. Let's see. I believe that's a 15 times 50. That would give me 750 and add to be 65, but it'd have to be a negative 15x and a negative 50x. So this would be 3x times x, negative 5 here, and a negative 50 here, and that does give me a positive 250. So I have 3x minus 50 times x minus 5 equals 0. So I actually have two solutions here. We have 50 thirds, or we have x equals 5. So we have to make sure we figure out where the maximum is actually occurring. So we're going to make a number line. So we have 5 and 50 thirds. And we're going to be plugging into the derivative. So this is the derivative number line. So if I pick, let's go with x equals 1. We'd have a negative times a negative, which would be a positive. Past that, let's say 6. 8. That's still negative, but that's positive, so overall it's a negative. If I pick something really big, x equals 100, I don't care. I know it's got to be past that. Positive, positive, so this is a positive. So think about what that means about our volume. It's increasing, decreasing, increasing. So here is my maximum value. So volume is a maximum when x equals 5 because the derivative changes from positive to negative. Let's see what the question actually asked us to find. Find the size of the corner square which will produce the container that will hold the most amount of soup. So the size of the corner square, that would be a 5 centimeter by 5 centimeter. Example 3. A rectangular page is to contain 24 square inches of print. The margins, the top and the bottom of the page, are to be 1.5 inches, and the margins on the left and the right are to be 1 inch. What should be the dimensions of the page so that the least amount of paper is used? The least amount of paper. So we're talking about area. So let's draw us a picture. We have a piece of paper. Here's a whole piece of paper. And we want to find the dimensions of that paper, so let's just be creative and call this X and Y. Talking about the whole page. But it tells us the dimensions of the margins. So we have margins going in. And this is the spot where the writing is going to be. This is the print going in the middle. So, let's think about the top and the bottom first. This whole page is Y tall. Top and the bottom, we're taking off 1.5 inches this way and 1.5 inches this way. So the printed part would be this total length, minus 1/2 and 1/2, which would be 3. For the printed part, this way, we had a total width of X, but the margins on the left and right are 1 inch each. So we take away 1, we take away 1. This is going to be X minus 2. Now, see why I'm putting that in here in just a second. Because our area, the least amount of paper, this is talking about the area of the whole page, which would have been that X times Y. But what we know about is that what is being printed. The 24 square inches of print is talking about this part, excluding the margins. So we know that X minus 2 times Y minus 3 gives us our 24. To be consistent, I'm going to solve for Y so that I only deal with X's in my problem. So if I divide by X minus 2, we get Y minus 3 equals 24 over X minus 2. And then all we have to do is add 3. So here's an expression for Y. We can use substitution to replace that Y with what it's equivalent to. So I get that my area is X times 24 over X minus 2 plus 3. Let's distribute. That'd be 24x over x minus 2 plus 3x. Now we have to take the derivative. I really wanted to make sure I did this one with you so we can review some of our rules for derivatives. This one we do have a quotient. So remember our quotient rule. The derivative of the numerator times the denominator minus the derivative of the denominator, which would just be a 1, times the numerator. Over the denominator squared. And then we have plus the derivative of 3x, which is just a 3. To be able to solve this, because we need to set this equal to 0, right? And we need to be able to solve that equation. So first I'm going to pretty this up. That's 24x minus 48 minus 24x over x minus 2 squared plus 3. 24x's cancel out. So I have negative 48 over x minus 2 squared plus 3, and we're going to set that equal to 0. Now I could have found a common denominator and all of that, but since I knew I was going to set it equal to 0, I kind of left it like this. Because what I can do is subtract the 3, turn that into a fraction, and now I'll have to do is cross multiply. I'll get negative 3 times x minus 2 squared equals negative 48. Divide both sides by negative 3. We get x minus 2 squared equals 16. Square root both sides. And so we'd have x equals 2 plus 4, which is 6, or x equals 2 minus 4, which is a negative 2, which is a bad answer. So x equals 6 is our possibility. Now remember, there's also a value that's going to make it undefined, which is 2. So when we go to test our derivative, which remember we're looking at a prime, I also have to test around 2, because that was a spot that could be a max or min 2. So if we plugged in 1 into our derivative, we'd have a negative. That would be positive. So we'd have negative. And if we tested here, let's say with a 3, positive, that's a negative overall. That would still be negative. Past 6, let's say 10. So it says 8 squared, be like 64. So this is actually a really small fraction now. It's smaller than 3. So now we'd be at a positive. So negative to positive creates a minimum. So area is a minimum. When x is 6, because the derivative changes from negative to positive. Don't forget to go back and figure out what the question asked for. It asked for what should the dimensions of the page be. So we need to know our x and our y. So we know we have our 6 inches. 6 inches by what? Well, we can find out the y by plugging into here. So 6 minus 2 is 4. 24 divided by 4 is 6. 6 plus 3 is 9. Next example. A rectangle is bounded by the x and y axis, and the graph of the line y equals 3 minus 1/2 x. What length and width should the rectangle have so that its area is a maximum? So that rectangle, its length is x, and its width up here is y. So our area is x times y. Well, the y value at any of that point right there is the same as the line right there. Y equals 3 minus 1/2 x. Substitution. That would be area equals 3x minus 1/2 x squared. And then we'd take the derivative and find where it's the maximum. So let's go ahead and do that. It's going to be minus 1x. And we want to find out when that equals 0. This one's super easy. X equals 3. Let's test it. So let's check when x is 1. Plug into here, 3 minus 1, that's positive. We plug in 5. 3 minus 5 is negative. The area is a maximum. When x is 3. Because the derivative changes from positive to negative. Have we answered the question? We want to know what the length and the width of the rectangle should be. So the length should be 3. And what would that make the width? Well, we'd have to plug it back into here. So half of 3 would be 1.5. So 3 minus 1.5 is 1.5. A solid is formed by joining two hemispheres to the ends of a right circular cylinder. The total volume of the solid is 12 cubic centimeters. Find the radius of the cylinder that produces the minimum surface area. So some of these, the hardest part is actually just setting up the problem. So first thing on this one would be to draw a picture. We have a right cylinder, circular cylinder. And it says that we have two hemispheres on each end. So we have a circle there and half a circle there. So if I put those two circles together, I'd have a whole circle, right? So let's think. Okay. First, we know something about the volume. So I'm going to go ahead and write down that. The volume would be, if two pieces of a sphere, so that would be a total of 4 pi r squared, plus the volume of the cylinder, that'd be pi. Oops, I'm sorry. I was writing surface area. Volume of a sphere. We should know that. That's 4/3 pi r cubed. Pi r squared h is the volume of a cylinder. Now the area, surface area, would be 2 pi rh for that wrapper around the cylinder, plus 4 pi r squared for the spheres. Now, I don't think you're going to have any problems actually taking the derivative and everything once you get there. What would stump you on a problem like this, I think, is figuring out how to combine the two so that you can maximize your area. Well, we're trying to find the radius that makes this work. So what I would do is solve this one for h. We know this equals 12. So pi r squared h equals 12 minus 4/3 pi r cubed. And one thing that would help is to get rid of that 4/3 there, just to make sure you understand how to make things a little bit easier to work with. Because I don't want a fraction within a fraction. That would get messy. If I multiply both sides by 3, first, it's going to make it a little bit easier to work with. Now you can use substitution to take this expression and substitute in for this one. Let's go ahead and see what happens when we do that. So 2 pi r times 36 minus 4 pi r cubed over 3 pi r squared plus 4 pi r squared. Now notice, when I multiply here, these pi's are going to cancel. This r is going to cancel out with one of these, so I'm going to be left with an r down there. So that really gives me, let's see, if I distribute what's left with the 2, that would give me 72 minus 8 pi r cubed over 3, and there's still an r, plus 4 pi r squared. The rest of this is just algebra. (72) divided by 3 is going to give me 24 over r, which would be 24r to the negative 1, minus 8/3 pi r cubed divided by r would be r squared, plus 4 pi r squared. What would be the derivative of that? Go ahead and try it on your paper. I'm going to write down the answer here so you can double check yourself. Once you've found the derivative, you're going to want to set it equal to 0 and solve. And this one is kind of an ugly one. So let's see if we can work together to figure this one out too. So what I did is I moved this fraction over to the other side, because it had r squared in the denominator. This one, they both had an r, so I factored it out. I'm still wanting to get it prettier, but this is a start. If I multiplied both sides by r squared, I'd have r cubed over here. And I'd have 24 divided by all of that junk. Which I wonder if I could get that a little bit prettier. Let's see. Negative 16/3. If I turn that into a fraction as well, 3 times 8 is 24/3. That's going to be 8/3. Now, dividing, so now we have a pi down here, but dividing by a fraction is the same as multiplying by the reciprocal. 8 goes into 24 3 times. So I'm left with 9 over pi here. So r equals the cube root of 9 over pi. And then we would test our values to the left and the right. I'm going to go ahead and move on to the next one for the sake of time, because I think you'd be able to test the values, and that actually is the radius that works. Some of them you don't need to draw pictures for. Sometimes it's just as simple as being given the equation. And on this one, we're given that formula, and we're trying to maximize profit. So we would just take the derivative, set it equal to 0, solve, and test some values. So I'm going to leave that one for you to do on your own. I wanted to make sure I got to the next couple of examples. In example 7, determine the point on the line y equals 2x plus 3 so that the distance between the line and this point is a minimum. So, if you remember anything from geometry, your distance would be at a minimum like this. It'd be the straightest line. So what we're trying to do really is find this point, xy, where this distance is a minimum. So I'll call this distance d. So let's remember distance. Distance formula. The difference of your x's squared plus the difference in your y's squared. So, x minus x, I'm going to write it as x minus 1 squared, y minus 2. The difference between this point and this point. Now, we've got two variables, so we want to use substitution. Well, we know the y value is 2x plus 3. So we're going to use substitution. Now, to be able to take the derivative of this, you're really going to have to clean things up. So we're going to have to remember our algebra. X minus 1 squared. That's x minus 1 times x minus 1. That's going to be x squared minus 2x plus 1. This is really going to be 2x plus 1 squared. That's going to give us 4x squared plus 4x plus 1. Pretty that up one more time. That's 5x squared plus 2x plus 2. So really, we have 5x squared plus 2x plus 2 to the 1/2. And we have to take the derivative of that. So this is a good one to practice taking the derivative of and remembering how to take the derivative of a chain rule. Derivative. Exponent comes down. To the negative 1/2 times the derivative of the inside, which would be 10x plus 2. Now remember, to the negative 1/2 means that that would be in the denominator, right? So we'd really just have 10x plus 2. Wait. Oh, half of that. How about let's combine that? Half of 10x plus 2 would be 5x plus 1 over the square root of 5x squared plus 2x plus 2. And we want to find out when that equals 0. Well, remember, a fraction can only equal 0 when the numerator equals 0. Remember, since this one is talking about a graph and we're not looking at a real life thing, a negative does make sense, and it does make sense when we look at the graph. If you plug in -1 into this derivative, you'd have a negative. If we plugged in a +2, it's going to be a positive. So this x value would give us our point that gives us our minimum. So we would want to find the y value that goes with it, and where would we look to do that? Oh, back to that equation. So it'd be the point -1/5, and then -2/5 plus 3, that'd be 13/5. The last example we're going to go through together. We have a rectangle ABCD with sides parallel to the coordinate axis is inscribed in the region enclosed by this parabola. Find the x and y coordinates of point C so that the area of the rectangle is a maximum. So let's go ahead and see if you can set this up. Hopefully you realized what I didn't realize. What's the width of that rectangle? Here's x, here's x. The width of that rectangle is actually 2x. Gotcha. Caught myself. So go ahead and see if you can find the maximum value. Now make sure you do the practice problems at the end of the section so that you're prepared for next class.